So, a brief introduction for Ali. Dr. Ali Zavabeti is a lecturer in the Department of Chemical and Environmental Engineering at RMIT University, and also adjunct senior fellow at University of Melbourne. He is actively doing research across range of multidisciplinary topics. His primary research interest lies in interception of liquid metals and 2D materials, electronics, and chemical engineering, with a focus on developing novel 2D materials and nano architectures for advanced nano device applications. Before entering academia, Ali served several years as automation engineer. So he has a strong industry background, brings a practical dimension to his academic work. Thank you, Ali, for joining us.
All right. Thank you so much, Naima and Mainak, for the opportunity. And thank you, Sam, for the inspiring talk. Just a disclaimer, this is a recently developed technology, so it's less than 10 years old. So some of them are adopted technologies, some of them not, and there's an ongoing research. So as Naima introduced me, my name is Ali Zavabeti. I got my PhD on liquid metals and looking at their surfaces, and also we successfully exfoliated 2D oxides from liquid metal surfaces. So to point in this direction. Okay, I just use it. Oh yeah, no worries. So the relevance, as Naima mentioned, I also used to spend some time in Australian papers down in Maryville, building the automation system for a de-inking plant. So that's the only relevance from my work to larger scale printing. And I try to bring these two together, basically. So I will just a little bit discuss about liquid metals. I'm pretty sure many of you know what liquid metals are, but I just briefly discuss it. I talk about unitary metals, just one metal, liquid metal chemistry, that is also very interesting to investigate, and then some of the opportunities and also challenges. And some of the recent work that we did in printing the 2D layers, basically. So what liquid metals are, basically the metals that are liquid near room temperature. We can basically melt all of these metals on a hot plate. So I created a query to basically on the table of elements to show the state of elements at 450 degrees Celsius. So that the blue ones, dark blue ones, are the ones that are in liquid form, so we can basically melt and print them as a 2D in room temperature. We are mostly, and the one with the red rectangle is basically the one that are room temperature liquids. So of course it's mercury, but mercury is toxic and also evaporates at higher temperatures, and rubidium, cesium, francium, they are prophoric or they are radioactive, so they are not really useful. So we end up using gallium and its alloys. And it's non-toxic, so it melts at 29.7, 29.8. So if you hold it in your hand, it melts in your hand. All right, so liquid metals mostly, they are mostly integrated because of their conductivity in application of flexible devices. Basically, you can use stretchable devices. That's the main thing that stands out from other coatings, that it stretches and goes back to normal because it's liquid. It just merges back. So two most investigated or utilized alloys are called EGain and gallium. So EGain is you take the gallium indium, which with the melting points of about 15.5, and gallium with a sub-zero freezing, which, you know, both of them stay liquid in the room temperature. So these are highly utilized in this type of applications and variables. Basically, the bulk liquid metal, generally speaking, mostly are passive compounds. They can be used as active compounds, but mostly are passive compounds. So, for instance, try to play this. So All right, so basically it can be used in stretchable, implemented in a stretchable devices. So they can stretch, and the stretchability basically is limited to, the PDMS or the holding substrate. So it can literally go basically 1,000% strain. And that can be used as pressure sensor, for example. So because as you stretch it, the resistivity drops, and then therefore you can measure the pressure and the stretch. Also, they have been used because they are biocompatible, they have been used as a pressure sensors and also as electrodes in bio devices. So what I'm trying to, where I'm going today is basically I'm trying to just focus on the printed layer of oxides from the surface of liquid metal. So that's my main focus of the talk today, which is they are most active compounds that we can use, and they are basically functional material that we can harvest for using in electronics, for sensing, and so on. So on liquid metals, similar to all other metals, there is a nano layer of oxides being spontaneously formed if it's in air, in room temp, in basically ambient condition. And that oxide layer is self-limiting. Basically, it grows and creates a barrier, both a physical barrier as well as builds up a potential across it that limits growth of the oxide layer. So it remains in nanometer regime. Again, one fascinating thing about liquid metal is a liquid surface is most atomically flat substrate. So it's really ideal for material, 2D material growth. So we have invented several methods for printing these 2D oxides. We started in 2017, 2016 by just touch printing, basically melt the liquid metal on a substrate, get a substrate, another substrate, touch the surface and delaminate. So we could harvest 2D layers. Then we came up with a slightly larger surface area printing. We called it squeeze printing. So we can place a smaller droplet between two substrates, press them. As the droplet expands, it forms oxide, and also at the same time, the oxide attaches to the substrate. So we can coat and print 2D oxides on this substrate. And also we invented roll printing. Basically, it's like a pen style. You can roll a droplet and you can basically write in two dimension. Again, we invented several different methods to also have them as a suspension as well. So I'll just play you a video of how we have done this. So firstly, touch printing. So you can grab a substrate and touch to a liquid metal, and then you've got a 2D material printed, as simple as that. Or you can basically squeeze, and then you get a larger area. But because you delaminate also liquid metal, you can wipe it in warm ethanol, so it can be easily cleaned. Yep, so again, another method is, as I mentioned, is squeeze printing. So you place a very small droplet on a substrate. You get another substrate here, glass. And then squeeze. As it expands, basically it prints a two-dimensional layer. So these layers are from 2 nanometer thin to 5 nanometer, depending on the oxides that we get. So basically here is 1.5 nanometer. The roll printing we invented for this specific mixture because the viscosity for this specifically was very high, and we had to drag it along the substrate. And also, to get in a suspension, we can just bubble gas, any reactive gas. Here, just oxygen containing gas, and then you can basically as the bubble rises, it forms a 2D oxides and then releases 2D oxides. Then you can basically drop cast. So here is the way that we can also clean the surface. If you squeeze, the alloy comes out from the other side. It's fresh. The surface is fresh, so you can again grab another substrate. Here a TM grid, because we need to also study these 2D layers atomically. Basically, we use TM to study, so that's the way we transfer onto a substrate. Oh, I think I jumped out. Okay, so when we check if, yep. So we printed a whole library of 2D oxides because we can melt gallium, tin, bismuth, zinc, and their mixtures. And then we show that we can post-convert them to nitrides, phosphatize them, sulfurize them, plasma convert them, and so on. So we achieved a whole library of two-dimensional materials that these materials are not actually achievable or possible in nature as a layered structure. So these are non-layered structure material achieved as 2D layers. So we can also change the surrounding gas to other gases. For instance, here is H2S. And then we can melt tin and touch a surface. We can get one of the best piezoelectric materials as a coating is SNS. All right, so would like to just briefly discuss about single metal against alloys. So what happens if you have alloys and if you have single? So for single metals, for instance, we have indium. We can squeeze print and we get highly crystalline. It's a cubic indium oxide. It's about 2 nanometer. Basically, the indium can melt at just above 150. So we place a hot plate around 200, just above 150, and we can basically 2D print these very nice indium oxide layers. For ITO, basically ITO is widely used contact material. Basically, it's a TCO, transparent conductive oxide. So we have shown that if you mix indium and tin, and then we squeeze print, we can get ITO as thin as just a few nanometers. So here is 1.5 nanometer. We can multiple print or just a single print, and we can basically, we show it is conductive. And we use touch screen in our publication, and this is being used with a different style. So in industry, they used to, like in Apple and Samsung, apparently they used to have a glass inverted and float onto liquid indium and then sputter tin on top to make ITO. However, they have changed their process slightly to also just, instead of doing sputtering, just to melt it together with indium. So they adopt, this is an adopted technology at the moment. So, and then there is also a chemistry involved with liquid metal. It's not just mixing two metals and get a complete mixture. So what we found out is we can, basically gallium can dissolve many metals. So we can basically very easily grind other powders into gallium, and therefore we can then harvest the oxide layer. So we tried that with hafnium, aluminum, and gadolinium powders, and we could achieve the surface mostly dominating by these oxides. So basically, again, this is a different chemistry than, and the way we harvest is a touch printing method. So we don't do squeeze printing. The reason for that is we need to allow enough diffusion for large atom gadolinium and hafnium to diffuse to the surface and react with oxygen. So here we had about less than 1,000 ppm oxygen and sufficient time to get very pure metals. But again, liquid metals giving us a unique chemistry that we can harvest multiple, like a large portion of table of elements in 2D. So we use the same concept. We mixed in tellurium and selenium. And then by doing that, we lowered the melting point. So the tellurium melts at 450, and some phases of tellurium oxide are not achievable within that temperature. So we reduced the melting point and printed tellurium oxide in beta phase, which is a high p-type mobility oxide. So basically, we made devices out of it. So they are a wide bandgap, high mobility p-type coating. So we can basically, that's a SiO2 substrate, and this is a printed, large area printed 2D beta tellurium oxide. So next is just a unique opportunities in liquid metal printing in engineering the skin, basically. We can also engineer the vacancy and doping and so on. So what one of my students did was the SNS that I introduced you earlier, that is one of our material of choice for piezoelectric material. He substitutionally doped indium inside SNS, so we could improve about 22.6% of the piezo coefficient, as well as we made gas sensors that we could basically detect NOx, NO2 in less than 2 seconds, which are really impressive. So I'm showing this because I'm basically would like to mention that this type of doping is generally not done in situ. So either they are done as a post-treatment by irradiation, but this is basically an in situ growth. So we mix them as an alloy, and then we print them as a single unit, single layer. So they are not really post-treatment. So they are in situ growth using liquid metal methods. And as I mentioned during the introduction of the liquid metal chemistry, the ratio of added element in the base liquid is different than what is end up in the 2D film because of the differences in Gibbs free energy of formation or the combustion energy. So we add sometimes very high ratio of less reactive material to get just a little bit of doping in the oxide layer. So the challenges we do have is solubility limit, so we can't really add a lot of material into gallium, so there's a solubility limit. Base liquid metals that we can melt on a hot plate are limited to basically maybe 5 or 6. But advantages is basically these are naturally grown layers without post-processing. So, and they're very easy to make. So it just needs a hot plate, a human, and basically it's just you combine these two and you can basically have a printed 2D sheet. So another opportunity is the doping. So we can change the doping of these layers. So we've shown that if we just add certain elements, there is a competition for them to come to the surface and appear as in the oxide. We can show that we can, for instance, for gallium, we can print N-type gallium, and then also by adding some elements, we can make a P-type oxide, gallium oxide, which is again great. So for defect engineering, what my students shown in the lab is also for printing 2D bismuth oxides. If you reduce the oxygen content to ppm levels, about 10 to 90, 10 to 80 ppm oxygen, and less than a second printing, you can induce you can break the centrosymmetry of the crystal structure. So bismuth oxide, this specific phase is a centrosymmetric crystal that doesn't have the functionality. For example, it doesn't have piezo or memory performances, but we could print in low oxygen ppm as well as very fast printing to disrupt the full growth of the oxide layer. So therefore, we basically broke the symmetry. So we made a non-centrosymmetric oxide layer. And we've shown that we can actually make self-powered devices out of it that are piezoelectric. And also, we used basically like a positive up, negative down measurement to show PE loops. So they are basically ferroelectric material from a material that intrinsically doesn't have that capability, which is really excellent, excellent to have. So again, liquid metal is offering a unique chemistry, a unique method of tuning the surface, engineering the structure, and so on. So this is a printed layer of bismuth oxide on SiO2. So we can program these printed layers as a memory device. So just using AFM-based methods, we can write RMIT logo. We can delete it, write square, again, delete it, and maybe read it a month later. That square is still there. So basically, it keeps the memory. So we could make functional devices. So as I mentioned, these technologies are very new. So we invented this in maybe 2016, 17. So the TRLs are low. However, there is there's an ongoing work to upscale these processes. So this is from groups in US. So they upscale these methods. One is in basically they publish in Science. This is one of the liquid metal leaders, Michael Dickey in US. They printed meter scale, so they can print meter scale oxides. And one group in, again, another US, also our collaborator, he's printing using a roller system. And just the recent work we did at Monash. So we tried at Monash to print using Naima's printer. So this is actually done by Naima. Yes. So at the moment, there is no liquid metal lithography technology. There is nothing that I know of, at least. So this is the first lithography using liquid metals printed at Monash, which is really great. So we can basically, we can show print shapes. And this is done through a mesh. So what Naima did was basically she put a mask above SiO2 and then pushed liquid metal through it using squeegee. And we could get these very nice arrays that, again, we have not done this before using liquid metal technology. We don't have any lithography methods, like a direct lithography. We still can do lithography, but using maybe photolithography or other type of lithography, or maybe using electron lithography. But using direct printing, we haven't done it yet, so this is the first time. Also, I would like to show you, it's just at the end of my presentation, just show you my students at the moment. He's also printing these 2D layers. So he's using a 3D printer to print in 2D. So that stretch is basically just a 2D oxide. And he just used a small pipette tip and a liquid metal inside. And this is a 3D printer that he just moves, and it leaves a 2D layer behind, which is really, really great. Yeah, so what happens is he goes forward, and there is a liquid metal residue because of the high surface tension of liquid metal. It just goes back to join the nozzle. Yep. So liquid metal printing. So we basically offer a wide library of two-dimensional materials as well as bulk printing. But especially for 2D printing that are functional layers, they are uniform, they are atomically thin, they are ranging from maybe half a nanometer to maybe 7 nanometers based on the parent metal. They allow in situ defect engineering, doping, and then also P-type, N-type charge doping. These methods are very fast, very simple, it's vacuum free. And of course, it is work in progress as well. I would also like to thank my collaborators and my mentors, and thank you for your time.
Thank you, Ali, for a very nice talk, like always, and thank you for passing the printer to me. It was you that, thank you for coming here and let us to do trial with these liquid metals. Actually, it was a sample of unsuccessful in screen print that we could benefit for designing the array, but we hope that we can continue together. So it's time to question, first from audience.
Is it on?
Yep.
Is it on? Yep, perfect. First of all, fantastic presentation. Thank you. I just wanted to ask, because I work with liquid metals as well, have you noticed what's the crystal quality difference between pure growth and liquid metal growth? Because from my understanding, liquid metals aren't as high quality as something like MOCVD.
Yeah, good question. So mostly, if it's done in low temperature, mostly amorphous. So there is actually sometimes no crystal. So it's just amorphous. Depending on the application, they can also be more useful than highly crystalline. But we have shown we can make them crystallize by annealing. However, a direct printing of like a room temperature printing usually results in poor quality crystal, but it's a very nice uniform amorphous sheet, but low crystallinity. So you're right.
And I've just got one more quick question. Out of all the sort of methods like squeegee method and the exfoliation method, have you seen any real difference in like physical damage? Is squeegee method less physical damage?
Yeah, it's actually a very good question. So initially we started as a squeegee, but squeegee on a single substrate, not through a mesh. So the problem with the squeegee was you get basically a patchy oxide. So if you have like you want to coat a large area, if you go like this, then you get patchy oxides everywhere instead of getting a uniform layer. So the best methods so far are basically the printings, the methods that the uniform printing method using non-manual device, and as well as the squeeze printing. So squeeze printing is very, very uniformly gross, and we get, if you are doing it manually, because fume hoods, if you do it inside a fume hood shakes and your hand shakes maybe, so you get wrinkles. It's on a liquid surface, so you get wrinkles. If you hit it too hard, you get ruptures. So basically, because it's a lot of work is done manually, there are some defects, manual defects also introduced in this work. So,
thank you for a fascinating talk. Look, there is a technology called, where you made plate glass, Pennsylvania plate glass process, where you use liquid lead as a bed, where you actually make glass, essentially. Now, what I was wondering is, among the methods which you have described, where do you see the potential of scaling up the manufacturing of this kind of oxides or even liquid metals? Because I think potentially it is scalable in terms of the history of using liquid metals for processing large scale. But I'm going to say it has to be tuned for sure. But where do you see, how do you foresee this technology being, making into large areas and stuff like that?
Yeah, so um, again, good questions. So far, the TRL is very low, but I'm very, very optimistic because of the importance of the materials that we are dealing with. For instance, gallium oxide is a wide bandgap semiconductor used in high voltage electronics, and then indium oxides, for example, ITO. And then we don't need a large quantity of this because we only harvest atomically thin layer. So there is always a problem with supply chain, but still because we are harvesting a thin layer, it's okay. And I don't see any problem in upscaling so much, but basically manpower and having, like something like this community to come up and help with someone like yourself to help with the larger scale printing. And I think the technologies can be easily adopted because these materials are flexible, because they are uniform, they are ultra thin, they can be easily integrated into flexible devices. So I see it very applicable in technology adoption, but not sure when.
Thank you.
Yeah, one question there. And then one online, right?
Thank you for the presentation. You have shown us like almost all liquid metals are silver in color. What if you want to make them colorful? Can you mix them with liquid color like food dye or something, or due to high surface tension they won't mix?
Yeah, so one of the limitation is, if I understood you correctly, is so liquid metals are immiscible in all of other liquids. So they don't mix in well with dyes, but certainly you can functionalize. We haven't tried functionalization of this material, but electronically, if you dope them, you can make LEDs. Basically, gallium nitride is a blue LED. Then we made in multiple ways. We made gallium nitrides, 2D gallium nitrides. We basically made several different like band gap variations of different 2D two-dimensional materials that could be used for LCD screens, for making LEDs, for making arrays potentially, but we haven't done yet. But post-functionalization, as far as I know, we haven't done integrated into any food dyes. So we use it as I use food dye together with liquid metal droplet to show in a fluidic system. So in microfluidics, how flow is directed. So to check the laminar flow going from one side to the other side, but it doesn't mix in well with the liquid metal.
Yes, we have one online question from Rance again. If Rance, you could unmute.
Yeah, really nice work, Ali. So I got two questions. The first question is, can you clarify if you were able to automate the squeeze printing method? And I guess a follow-up question to that is, were you able to identify like an optimal pressure to achieve like really uniform surface?
Yeah, thanks, Trans, for the great question. So we have not automated this. The Newton force that I'm shown on the slide is because of the question raised by one of our reviewers that what force do you apply? And then we basically try to use just a general, like we use a general tapping hand tapping, and then we figured out that's 2 newtons. But this has not been done automatically. So all of the work that we are currently doing is mostly manual. Yeah, hopefully soon, but all of it is done
Yeah, I
manual.
could see if you automate the process, it'd be great. Yeah.
It will work very well. It should work
Yeah.
very well. The squeeze printing a little bit sometimes become messy. So you need to make sure that you dip the substrate into a warm ethanol and use a very, very soft, basically cloth to wipe and then reuse the base liquid metal again in the next level. But it can definitely be automated, but we haven't done it, unfortunately.
Thank you very much, Ali.
Excellent. Thank you.
Thank you again.